Mhm. Okay. Can you hear me, Molly?
Yeah, I can hear you.
It might just be you and me today. Everybody keeps emailing me and asking me to record class.
Okay.
Well, let's see. We are in what chapter are we in? No idea. Looks like we were doing. See, we got all the way through chapter 8. So now we're in chapter 9, right?
Yeah, that's right.
Okay. Any questions from chapter 8 or anything from the labs or anything you want to talk about before we get started?
I don't think I have any questions.
Okay. Let's see here. Well, let's go ahead and get started then. Let's take a look at chapter 9. Trying to remember if I actually, shoot, that's not what I want to do. There we go. So we get, okay. So we're going to do chapter 9 this week, chapter 10 next week, and then we have an exam for chapter 6 through 10, I believe. And then we'll go from there. So that'll take us to the middle of July-ish. That leaves us about 2 weeks where we can cover fluids and maybe even squeeze in something on temperature or hearing or something to get us some variety here at the end. We'll see how it works out. So statics and torque is where we're at. Let's bring up the book. There we go. Can you see my textbook there?
Yeah, I can.
So this is a great demonstration of what this chapter is about, except that it's not the ideal one. They take this picture of this rock balancing in Kings Canyon in Australia, but if you go to Utah or Arizona, you'll find so many better examples of rocks balancing on top of other rocks. And it's interesting to note that these balanced rocks have in many cases been there for hundreds or thousands, sometimes even millions of years, just sitting there perfectly balanced, not falling over. You can tip them over. There are people that actually go into these places and tip them over for fun. It's not exactly great for nature, and it's also just not safe for anybody that might be down below, but people do things like that. So they are really balancing. It's not like they're cemented in place somehow. Uh, and this balancing is because of forces that are pulling different parts. You could think of it as forces that are acting on different parts of the rock in different ways. Up to this point, we've discussed forces as if they always act just on a single point on an object, and in fact we've reduced objects to a single point just to make that very clear. We've made it very simple, but of course we know that a car is not a point. We know that a hippopotamus is not a point. And so we have to figure out a way of doing our forces, dealing with our forces, and even our accelerations as if they're more realistic objects that they're acting on. You go up to somebody and you push them. Let's say you go up to somebody and push them right on the shoulders, and they don't accelerate just forward. They actually rock backwards. They kind of twist backwards a little bit. There's a lot more than just a forward acceleration from that forward push. And that's because of the shape of the person, the weight distribution of the person, where you push them, the angle at which you push them, the friction of their feet on the ground, all kinds of things, the bending of their body as you push them. There's a lot more complexity to this. And so we have to start adding a little more complexity in to understand it a little bit better and to be able to kind of take our understanding into the real world. So that's what we're going to do. We're going to start off with this idea of balancing forces, which is something that we call equilibrium. When something is balanced and it's not moving, we call it static equilibrium. Static meaning not moving, equilibrium meaning all forces are adding to zero. And one other thing that we're going to learn about in a minute also adds to zero, something called torque. So the first condition for equilibrium is going to be the forces all add together to equal zero. I just said that. That means that the forces in x have to add to zero and the forces in y have to add to zero. And there's going to be no acceleration whatsoever. And this is true for static equilibrium, where a person like this is standing on the ground and they're not moving and they're not accelerating, and that's static equilibrium. The weight of the person, which acts at their belly button, as if it's at their belly button or close to it, is counteracted by normal forces, which should be pushing upward on his feet. This should be cut in half, and one of them should be pushing on each of his feet. And those forces cancel each other out in this up-down direction, or this, y direction, whatever you want to call it, vertical direction compared to the ground. In this situation, you have a car that's moving along at a constant velocity, so it's not accelerating, which means the sum of the forces in the direction it's moving are zero. The applied force of the wheels on the ground on the wheels, the net force of friction backwards, the force of friction backwards, the net force equaling zero means there's no acceleration, so it's constant velocity. And then here they got the normal forces right, where the weight of the car acts at the center of gravity of the car, and the normal forces act on each of the wheels. And the four normal forces add together to equal the weight of the car. Otherwise, the weight of the car would overcome the normal force and it would fall through the ground. So the sum of the forces in x equals zero, the sum of the forces in y equals zero, equilibrium. Ta-da. But that's only the first condition of equilibrium, because in equilibrium, both static and dynamic, this is dynamic equilibrium where the thing is moving, this is static where it's not moving. But in both of those situations, you also have to make sure that nothing is rotating or nothing is experiencing rotational acceleration. So if something starts off not rotating at all and then it's rotating after you push it, then that is accelerated in a rotational way. So there's something that we call angular acceleration or rotational acceleration involved here. So you take, for example, this hockey stick. If you apply forces like this, where if you draw a line between the forces, both forces are on the same line. That's called those are called collinear forces because they're on the same line. So if you have two collinear forces acting on an object, then they can cancel each other out completely. If they're equal and opposite, they can cancel each other out, and that's fine. And you have net force is equal to 0, and it's in equilibrium. In this case, however, you have the same two forces. They're equal and opposite in direction, but they're not acting collinearly. This one does not line up with this one, and you can see what will happen. The top one is going to cause this top of the stick to rotate kind of in this clockwise direction. The bottom one's going to cause the bottom of the stick to rotate in this clockwise direction. And you're going to get an overall clockwise rotation of this hockey stick at this point from these two forces acting on it. So the net force is equal to 0, but there's some rotational acceleration. Starts off with no rotation, ends up with some rotation. So there's you got some angular acceleration or rotational acceleration involved there. Forces that cause a change in rotation or an angular acceleration, we often calculate something that we call a torque to describe these forces that cause rotational motion, or that cause a change in rotational motion. Torque is not force. Torque is related to the force that causes this rotational acceleration, but it is not force. Torque takes into account more than just force. Torque includes the force that causes the rotation change, but it also includes some of the things about the force that caused it that can change the rotational quality or quantity or the rotational acceleration overall value. So what does that mean? Well, let's take an example that we're pretty familiar with, opening a door. Here you have 6 situations where you open a door, and you notice that in A here, you have a strong force or a bigger force acting out near the handle, and here you have a smaller force acting near the handle. So what happens if you have a big force and a small force on a door? Which one causes the door to open more quickly? The big force or the small force if they're acting at the same place on the door?
The big force.
Big force, right? That's obvious. You push harder on the door near the handle, and it's going to open up faster. If you push softer on the door near that same place, then it's going to open up more slowly. That just makes sense. What happens if I change the position at which I open the door? What if instead of pushing at the handle with this strong force, I take the same strong force and I push near the hinge? I don't like it right here in the middle because it's not as obvious in the middle, but if you're really close to the hinge, how hard is it to open the door?
Is it like near impossible?
Really hard. You've probably done that where you've tried to open a door for somebody when you're on the inside and the door is opening out, and you have to kind of hold that near the edge of the door. It's really, you have to push really hard to open the door, or to open the door at all. I mean, to do anything with the door, you have to really push hard. So this same force that made this door open easily is not going to open it so easily over here. So what have we learned here? We've learned so far that the strength of the force matters when you're when you're rotating something, but also the placement of the force relative to the rotational point. As you get further away from the rotational point, it turns out it's easier to open the door or cause something to rotate. As you move the force closer to the rotational point, it turns out that it's a little bit harder. And so that affects things, right? It's the same force is not going to open the door as much or as quickly as it's closer. Well, there's some other things here too. What if you push at an angle? Again, this is something we do when we hold the door open for somebody. We often push the door from the corner near the hinge, and our hand is not pushing 90 degrees to the door because our arm is sticking out almost parallel to the door. And what happens when you're not pushing directly 90 degrees to the door? Does it make it harder or easier to open the door?
It's harder.
It does make it harder, right? That's another reason it's really hard to open the door from the hinge side, because it's hard to get that 90 degree to the door kind of angle. especially if somebody's trying to go through the door, right? So um, angle matters. You've got the strength of the force matters. You've got the position of the force matters relative to the hinge or to the rotational point, and also the angle with respect to the force and whatever it is you're pushing on also matters. Here's the extreme example. The extreme example is, what if you push at an angle that is parallel to the door? Well, that just tries to pull the door off the hinge, right? That doesn't actually rotate the door at all. And so if you go to that very, very extreme angle of 0 degrees between force and door, then all of a sudden you have absolutely no effect on the door at all, no matter how hard you push or pull. So 3 things: strength of the force, position of the force, angle of the force matters. The torque is going to be a combination of all 3 of those things that will tell us how much something is going to accelerate rotationally, depending on the strength of the force, the position of the force, and the angle of the force relative to the object that is causing to rotate. So we define the torque as, in this equation, RF sine theta, where R is the distance between the point of rotation. And it doesn't actually have to be you don't actually have to measure from the point of rotation. You can measure from anywhere you want. Most people just measure from the point of rotation for convenience sake in physics. But R will be our distance. The F will, of course, be the force, and the sine of theta is going to be our angle. The theta is going to be our angle. But there's some very specific ways that we look at this, that we use these. And the reason for that is mostly because of the angle here. That's the thing that really matters. Where do you measure that angle from? So let's go to this example with the hockey puck or the hockey stick again. We're going to nail down the hockey stick at this point now. And we've got this force applied over here. R is going to be a vector in this case, and I'm going to draw the vector. They don't, but R is going to be a vector. It's going to be the position vector from the rotational point out to where the force is acting on the hockey stick. So that's my R vector right there. Go ahead and label it as the R vector. I'm going to call it R vector right here instead of just R. So that's the R vector, and it goes all the way out to the force vector here. The force vector is pushing on this side of the stick, and you can use actually either angle here. It doesn't matter which one you use for theta. It will give you the same answer. The sine of this theta and the sine of this theta will be the same. But that's the angle that is the theta. It's the angle between the R and the F as you draw the R vector from the point of rotation out to where the force is. Now, I said it doesn't matter where you put your R, and it doesn't. You could actually measure R from this point here, or this point here, or this point down here. It wouldn't matter where you measured it from, as long as you use the same point for every single torque measurement in this problem. So you can measure, if you have a coordinate system that's set up over here where this is 0, you can measure everything from here. The reason it's convenient to set it up here is because any forces that might be acting on this nail, and there will be some, are not going to have any torques involved, and so it just makes things simpler. And you'll see why that is the case in a few minutes here. You'll see why it's convenient to choose your point at the point of rotation often. Not always, but it's often very convenient. So there's our R vector. There's our F vector. There's our theta angle. Now we have everything we need. The R vector is in the equation, torque equals RF sine theta. You don't need the vector. You don't need any of the vectors. You just need the magnitudes. But you do need to know where that theta is located so you can make sure that you've got it correct, that you've figured out that angle correctly. So in the equation, it's torque. This is the letter tau for torque. Tau is a Greek letter, it's not a little t. That's tau. So when you're doing your homework and you have to use tau maybe in some problem, possibly, it's TAW. You can just spell it out, I think. Or you can look in the little Greek symbols thing. It should be in there. That's tau. But anyway, when we're going into this, when we're going to calculate this, we need the length of R. So you're going to actually need the length of this vector. Whatever the distance is between here and here is going to be the magnitude of R, which is R without the vector sign over it. It's the magnitude of R. And then you'll need the magnitude of the force, whatever that strength of that force is. And then the angle between the two, you put into the sign, and you have now calculated the torque. And the torque tells you, essentially, a bigger torque causes something to rotate or to accelerate in a rotational way more. And a smaller torque on a particular object will cause a particular object to rotate, accelerate in the rotational way rather less, angularly accelerate less. The units for torque are the Newton meter. It's force times distance. So it's just Newton meters. There's no other name for it. See if I can get my, there we go. Torque, so torque is actually a vector, but we don't really talk about it as a vector in this class because the vector mechanics of it are too complex. But we do talk about its orientation or direction or its sense. Often we call this the sense of it sometimes. But really what it means is that which direction is this torque going to want to cause things to change their rotation? In other words, which direction would it cause something to angularly accelerate if the thing was starting from rest? And so with this hockey stick here, you can see that this force is going to cause this thing to rotate in a counterclockwise direction. So we would call the torque for this one, we would say that it's in the counterclockwise direction. And torques that are in the counterclockwise direction, we usually label as positive. And then this torque here, you can see the nail, we've moved it up here, and this force is going to create a torque that's going to cause this stick to rotate in the the clockwise direction, which we generally label that as negative torque. So positive torque is counterclockwise, negative torque is clockwise. It's just the standard that we use. So this takes us now to the second condition of equilibrium. In equilibrium, we want all of our forces to add to zero in all dimensions, x and y and z if you have it. We're not going to deal with that, but you want all those forces to add up to zero so that you have no linear acceleration. But equally important, you also want all of your torques to add up to zero so that you have no angular acceleration. You don't want this thing to start twisting or to change its twisting motion or whatever else. It can be already twisting, but if you add a torque to it, a net torque will cause it to change how it's twisting because it will cause an angular acceleration of some kind. So there's our second condition. Total, these two conditions will give us three equations. Two equations for the net torque, for the net force equals zero, because you'll get an equation in x and an equation in y. And we saw that right up here, maybe in the last section actually. But we did see in the last section where you have the sum of the forces in x equals zero and the sum of the forces in y equals zero. Two separate equations. And then here you have the net torque equals zero. This only gives us one equation because torques always exist in a two-dimensional world already. So this takes care of both dimensions, this one equation. So simple example, you got two children on a seesaw, right? If you've ever played on the seesaw balancing game, whatever you want to call this thing, you know that a child who is maybe a little bit heavier is going to win if you place them both at the same distance. So if we put both of these distances, R1 to mass 1 and R2 to mass 2, were the same, but mass 2 was much larger, as it looks like she might be, then you're going to have this situation where the torque caused by this child is going to be bigger than the torque caused by this child. It's bigger because the weight is bigger and their R's are the same and the angles are the same. The weight is as acting downward, straight downward, so it's going to be a 90-degree angle between the weight and the R vector here. It's 90 degrees. 90 degrees here, same thing. But her weight is much bigger and his weight is much smaller. So you're going to get this unbalanced torque situation. But if you move these children around, instead of being at the same distance or at different distances, then you can actually have something balance out. You can have this this equilibrium condition met. How do you do it? Well, now you have bigger weight from two there, from child two. Let me get my drawing tool out here. Here we have a bigger weight, which is a bigger force, but a smaller distance, right? Here you have a smaller weight and a bigger distance. Well, can a big weight, or can a small weight times a big distance plus a small weight, or sorry, a big weight times a small distance ever equal 0? Well, yeah. If you multiply a small number together and get a time a big number, and you get a number like 8, because these two numbers are 1 and 8, for example, if you have a small weight of 1 and your r is equal to 8, 1 times 8 is 8. But if you have a bigger weight, where the weight is 8 and the r is 1, or the weight is 4, maybe that's much more realistic, I think. It's not even that realistic. But if you have a weight of 4 and a distance of 2, well, 4 times 2 is also 8. So these two things can add together if they can add together to equal to 0 if one of them is negative. Well, how do we tell if they're negative? We tell if they're negative by how they would rotate the seesaw. This kid is going to rotate the seesaw in this direction, which is the counterclockwise direction. Counterclockwise is always positive for us. So this one's going to be positive. This girl is going to cause this thing to rotate in the clockwise direction, which is always going to be negative. So this one here is going to be clockwise negative. So sorry, I put my line in the wrong direction. Clockwise is going to be negative. So we put a negative in front of this one, you get a plus 8 minus 8 equals 0. And then you have those conditions are now met. Right here. It's not very cleanly done. But anyway. So that's the basic idea behind this whole equilibrium thing. You now have another equation to deal with when you're dealing with things that aren't moving, not accelerating. They actually do the example here with the seesaw. They give us the mass of each child, and they give us the distance that the first child sits from the pivot. They give you the mass of the second child, but not the distance the second child sits from the pivot. And they want you to calculate how far the girl needs to sit from the middle in order to balance this out. Well, in this particular example, they're going to set up the equations right away. They're going to set up the torque equations. They're going to calculate the torques from everything. So we have the torque from first child, which is going to be mass first child times gravity. That's the weight of the child, so that's the force, times the distance. We also have to multiply by the distance. This distance here, which they give us, is 1.6 meters from the center. We're choosing the center point to be our measuring point. And then the angle between the weight and the force is 90 degrees. So it's just weight of first child times the distance that the first child is from the center there. And that's what they're doing here. R times weight 1. Weight 1 times distance 1. R times 1. R times times, they're using a W there actually. So R times W. Similarly, the child on the right side is going to have a torque equal to negative R2 times W2, because that one causes the clockwise movement, which is going to be negative. So this is this is the torque of child 2. But there's also a torque to calculate at the pivot, because the pivot also has a force on it. These two children are pushing down on the seesaw. Where the pivot is pushing up on the seesaw. But how do you calculate the torque of something that's right at the point where you're calculating your torque distances from? Well, you do it the same way you do everything else. Torque is equal to distance times force of the pivot, but the distance from the pivot to where the force on the pivot acts is 0. So it ends up being the torque at the pivot equals 0. And that's one of the reasons that you would set up your torques to be, or the distances to all of your forces for measuring torques or for calculating torques. That's one of the reasons you would set up your point of reference where you're going to measure from to be your rotational point, because if it's your rotational point, any forces that act at the rotational point are not going to have torques. Less torques, fewer things to calculate. We like that, all right? So here we've got our numbers. Yeah, here we go. Here we've got our numbers, our masses. We've got our distance of our first child. We're going to calculate the distance of the second child. Here we've got our equations. We know that the torque that's created by the first child is this. The torque that's created by the second child is this. Always a good idea to do these things symbolically first and then solve them later in equation, by plugging numbers in the equations. And then we have the torque at the pivot. All three of these torques have to add to 0. And so they do that. When they do that, they get torque 1 plus torque 2 plus torque P equals 0. And then they solve the whole thing for torque 2, and they find out that they find out first that the torque at P is equal to 0. And then they find out that torque 2 has to equal negative torque 1. Well, great. That means R2 with W2 has to equal R1 W1 because originally we know that we knew that torque 1 is going to be negative. So we put that in there, right there. So we get this equation. It's the relationship between the distance to child 2 and their weight, and the distance to child 1 and their weight. And if you solve this to solve for R2, which is the distance to child 2, you get this following equation: the distance to child 1 times mass 1 over mass 2. That's all you need to know. Plug in your numbers, calculate R2 to be a little bit shorter, and that's exactly what we expected. We expected the heavier child to sit a little closer to the middle so that their torque isn't quite as big, so that they can balance out that angular force in that problem. Then they asked for the force at P, and it's actually pretty easy to do because it's the force at P is certainly a upward directing force because it's counteracting these two forces, and these children are just sitting here, not accelerating through the ground or flying off into space. So that becomes quite easy. You're just going to add all the forces in y direction together, and net force in y equals 0, set them equal to 0, then solve them, right? Here we have the force at the pivot equal and minus the weight of the seesaw, weight of, not the weight of the seesaw, the weight of child 1 minus the weight of child 2. Those are the only three forces they define in the y direction. If you take the force, you take the weight of that, or the force on that pivot, subtract off the two weights, set it equal to 0, you should end up with enough to calculate your pivot force. Why? Because the pivot force now can be solved for by adding the weights to each side, and the weights are known. We know what the weights are. It's simple. So force of the pivot equals mass 1 times gravity plus mass 2 times gravity. Now you should be able to figure that out from the picture too, because in the picture you only have two forces pointing down and one pointing up. So force P has to equal weight 1 plus weight 2, and that's exactly what they got to. All right, that takes us to section 3. Section 3, they talk about stability, but we can't really calculate any stabilities. To calculate stability in a situation, you really have to do some pretty high level differential equations stuff. You have to do perturbation theory essentially. And I don't think I ever did the math for that until I was a graduate student. So that's pretty high up in the math world. Here they have, I've always thought this picture was weird because it looks like this dad is balancing their child. But in the picture, they tell you that it's a doll. Of course, it looks like a child because the doll is looking at him. Looks like they're having fun, whatever. But it's actually not that difficult to balance things. Even complex objects aren't that difficult to balance. And why is that? Because you can kind of move them around until you can feel them falling in gravity. Once they're falling in gravity, you know that there's an imbalance in forces on the object, and that's what pushed it over. And you can feel that with your hand. Your hand has very good tactile abilities to feel that kind of off balance thing, and so you can move things around. I have personally balanced a bicycle on my chin, and a big bicycle, not a little kid's bike, a really big, a full size like adult bicycle on my chin, from on the wheels. In fact, it's not terribly difficult. You're just counteracting that object trying to fall over, and you can feel that. It's fine. Sometimes it can be a little complicated because it's not always intuitive which way to go to fix that. But hopefully this kind of give you an idea. Here's an object that is in equilibrium. It's not going anywhere. It's just sitting here. And the equilibrium is a type of, there are different types of equilibrium, you could say, because of this idea of stability. If you push the pencil over just a tiny bit, just a tiny bit, it will actually kind of rock back and forth and just settle back into where it was. Now, it has to be a very short pencil. It has to be a very flat end on that pencil that you're balancing on, so on and so forth. But in the end, what's really happening is that if it's going to tip over, the center of gravity of the pencil has to be outside the tipping point. Because once this force here is outside the tipping point, then it's gonna have nothing to counteract it. Inside here, when the weight here is inside that tipping point or inside the pencil on this side of the tipping point, these two forces are actually causing the pencil to rotate back this way. They're causing this clockwise rotation. Whereas if this weight comes out here, both of them are going to cause counterclockwise rotation, which is away from where it was balancing, which means it's going to fall over. You can also theoretically balance a pencil on its tip. But in this case, no matter which way you move it, no matter how much you move it, these two forces, these two things here are going to go, are going to cause this thing to fall over. Why is that? Well, because immediately, as soon as you tip this, it's causing rotation all the way to the ground, and there's nothing to counteract it. And if you push it the other way, it's the same thing. And that's actually kind of what we did mathematically to figure out stability when we were learning about it. We actually took the equation that described the forces. There's the equations that describe the forces in 3 dimensions, 4 including time. And then we perturbed them a little bit. We just actually added in a little movement into the equation, just one little movement back and forth, and see if the equation stays true, if it stays stable. If it doesn't stay stable, then you know that it wasn't a very stable system. So this would be called, I think this is called, so this one's called stability for sure. This one I don't think is called stability at all. I think it's just considered unstable, because no matter how much you push it in any direction, it's going to fall over. It doesn't even matter if you just push it a little bit, it will fall over. Here's a situation in which the pencil won't fall over, but it's also not necessarily stable equilibrium. So this is stable equilibrium, this is unstable equilibrium. This, what is it? Well, it's laid down on the table so that if you push it, it rolls. So it's not really like stable. It's not really even, I mean, it's just kind of whatever it's doing, just kind of rolls until it slows down from friction and ends up in the exact same position it was before. In this case, both of these forces, the weight and the normal force, move together. They travel together as the thing moves. And that's why this happens. That's why this works out. So this one's called neutral equilibrium. It's neither stable nor unstable, and it's not really even equilibrium. So they call it neutral equilibrium. And you can do some experiments with this. If you've ever been an athlete, you know that your ready position in sports is usually with your feet spread apart a little bit and your knees bent. And what does that do for you? What that gets your body closer to the ground. You get your center of gravity close, really solid between your 2 feet to make sure that you don't fall over. Because if you're standing up, it's much easier to get this force outside of either of these normal forces because you have a longer lever arm here, and that makes it less time and less space for you to fall over if you stand up straight. If you crouch over though, you have to actually rotate through a bigger angle to get this outside of this. Here's a chicken. The chicken has a body that's fairly low to the ground with legs that are fairly well spread apart. Also, it's a very stable condition. And that's pretty much all we're going to talk about there. All right. Halfway through. Well, how are we going to use these tools now? We've got the conditions for equilibrium. We've learned about how to calculate torque. We've learned about the directions of torque. Counterclockwise is positive, clockwise is negative. We've done some simpler problems. How are we going to do some more complex problems? We're actually going to do them the same way we did the force problems from chapter 4 and chapter 5. And this system up here is pretty much the same way. These steps where they draw a picture, they label all the forces. But in this case, your picture is not going to go to a point when you go to your free body diagram. Your free body diagram might be a line now or some shape where you can have forces acting on different parts of the shape instead of just treating the whole thing like a point. So that's the only real difference. But then you go through and you solve your equations. You've got 3 equations now. You've got one equation for the sum of the forces in x equals 0, another one for the sum of the forces in y equals 0, and then the last one for the sum of the torques equals 0. So you have 3 equations, and you can use all of them simultaneously to solve for anything you don't know. And that's pretty much it. So here's a pole vaulter. He's holding a pole up. He's got this force here, the weight of the pole down this way. If he slides the pole over a little bit, so the center of gravity is still between his hands, he can still hold it this way, but since the center of gravity has moved much closer to his right hand has to do more of the work to hold it up. So it's bigger force on his right hand than on his left, and the weight is still pointing down. If you go out here to the end of the pole, then you have to switch the grip on one of your hands. You can see here that the back hand, or the hand that's further away from the center, has been switched over so it's palm down, and this one is still palm up. Why? Well, because the weight of this pole is going to try to cause this thing to rotate in this clockwise direction. We need to put a force on this that's going to try to rotate this thing in the counterclockwise direction to cancel out all that clockwise direction stuff. And it's a lot. So you actually, and since your hands are much further away from wherever point you're going to measure from, you can actually hold up. You're actually holding up. You have to. This is like the hinge on the door right here, and our hand is very close to the hinge on the door. So we have to apply a much bigger force here to hold up this pole than we did up here, or we did here, because here both of our hands are closer to the end of the pole. These and this one, our hands are pretty well. They're kind of in the middle, so they're distributing pretty much evenly. But this one, you're way out on this end, so this force down here has to be pretty big to rotate this big long lever arm very much using this tiny little lever arm. Oh, excuse me. So, excuse me. I always get warm really easily when it's really, or sleepy really easy when it's warm outside, even if I'm in an air-conditioned house. So we have this problem here. We're going to. This is the second picture actually. Yeah. So this is this picture right here that we're doing. And they tell us that we've got the force exerted by the right hand is FR, the force exerted by the left hand is FL, and the hands are 9.9 meters apart, and the center of gravity is 0.6 meters from the left hand. Right. So this is the situation we're in. Let's draw a picture. Instead of a free body diagram with a point, we're now going to draw our pole here. And then the center of gravity is going to be right in the center of the pole. And they tell us the forces. So this is the weight of the pole is going to go down. Weight of the pole. We've got, let's see, where did that, oh, I missed it. There we go. So our distance between the hands is 0.9, but the distance at the center of gravity is 0.6 meters from the left hand. So if we're facing this person, their left hand is on this side and their right hand is on this side. We know that it's 0.6 meters from their left hand, so we call this distance 0.6. Here's the 0.6. And since it's 0.9 meters between both their hands, then we know this one has to be 0.3 because 0.6 plus 0.3 is 9. So now we have the distance from the center of gravity of the pole to both hands. And that's good. So what we're going to do is we're going to start with the torque equation. The torque equation first says that the torque of the person on the left, which we're going to call 1, plus the torque of the person on the right, which we're going to call 2, plus the torque. Let's see, where can't remember the picture. Well, this is the yeah. So the plus the torque at the center of gravity point. Put the torque at the center of gravity. Center of gravity, CG. There we go. It's terrible CG. Those three torques have to add together to equal 0. Well, if we measure everything from the center of gravity, then the torque at the center of gravity is going to be 0. So that one becomes 0 because the distance from the center of gravity to the center of gravity is 0. So the R times F, the R is going to be 0. There's no torque here. And that leads us to this equation. If we the torque 1 and you subtract torque 2 from it, you get this one being torque 1. It's the clockwise torque, and this one being torque 2. Torque, net torque. Yeah. Sorry. So anyway, they're actually doing this problem a little bit differently than I thought as I'm looking at this more closely. But essentially torque 1 plus torque 2, torque 1 being this one, torque 2 being torque 1 being from my left hand, torque 2 being from my right hand. So we might actually label these as torque left and torque right or whatever. And the reason that they've got it differently here is they're saying that the torque in the clockwise direction equals negative the torque in the counterclockwise direction, which is also true. If you're going to have something not rotating, then you have to have some clockwise and some counterclockwise, and those have to be equal and opposite. But it doesn't really matter. In the end, you find that the torque from your right hand see. So the torque from your right hand is going to equal the torque from your left hand, which is true. And there's a negative on there. And so they actually do those. They actually can calculate those. Now in this particular case, they're see, what are they measuring from here? In this case, they're measuring everything from the left hand side so that the torque at the left hand goes to 0. And that's fine. So they measure everything from where his left hand is, which would be this right hand for us looking at him. My picture, oh, I left my picture out. So anyway, so they end up with, instead of a 0.9 and a 0.3, they end up with a 0.9 and a 6. And instead of a forced right hand, forced left hand, they end up with a forced right hand and the weight of the bar. And that works too. It doesn't matter where you measure from, as long as you measure your torque distances all from the same spot in the same problem. And that's what they do here. So you end up with this equation. Notice that the minus sign went away because this one ends up being a minus torque because it's going clockwise. Then they just solve this for the force on the right hand. 32.7 newtons. Once you've got that, that's the force the right hand is pushing up with, then you can use the forces in the y direction. In the y direction, you have the left hand force up, the right hand force is up, both of those are positive, minus the weight of the bar, which is down, equals 0. You just solve for the force right, and you know the mass of the bar, so you can calculate the weight of the bar. Then you can calculate the force on the left hand from that. And that's all she wrote for that example. Did you follow that, or do you need any extra explanation or anything? Good to go?
I'm good to go.
All right. Second to last section. Here we talk about machines. Machines are objects that take advantage of this whole torque thing because you can, essentially. Here's an example of a very simple machine, the pry bar. You have a rotational point right here where the pry bar is hitting this floor or piece of wood or whatever it is. And then you have two things that are two ends of this that are rotating as well. You're rotating around that point, essentially. You have the long lever arm part where you put your hand on the pry bar, and then you have the short one here, which is the one that you put on a nail or whatever you're pulling out. We apply a big force here, and we get an even bigger force down here. Why? Because we have a big distance here, and we have a small distance here, but these two things have to be equal if they're going to add to equal 0. Now you say, well, what if this thing starts to rotate? Well, it does start to rotate, but we can say right up until the point it doesn't rotate, it's static, and it's not rotating, it's not accelerating, whatever else. And even after it starts moving, if it moves at a constant angular velocity or a constant rotation, then it's still going to be equilibrium. So we can use the equilibrium equation here, essentially set them equal to each other. When we do that, we actually can calculate the ratio of the forces, the amount of force that comes out, or the amount of force on the nail, divided by the amount of force that we put in with our hand. And we call that value the mechanical advantage. And you can just use it if you know what the forces are. If you know that there's 10 pounds of force on the nail and 1 pound of force on your hand, put in 10 over 1, you get 10. The mechanical advantage of 10. So on. And here they actually go through and solve that. You can also do it for the lengths instead of the output over the input. It's the input over the output lengths for the mechanical advantage. And this works for any tool. Here's a wheelbarrow. You can also do it for a wheelbarrow. In the case of the wheelbarrow, the lifting up on the handle is your input force. The output force is how much weight you lift in the actual container of the wheelbarrow. With a shovel, you can do the same thing. But with a shovel, you're going to have the weight of the dirt and the force on the handle. So here they do the mechanical advantage of a wheelbarrow. You need to know the force that you apply to the wheelbarrow, force in, the force that you're lifting in the wheelbarrow, the length from the rotational point, usually at the wheel, to the output force, and the length to the input force. Plug them all in. Now here's something interesting that happens with a particular kind of machine, but it's different in that it's not a lever type machine. It is technically a lever. Wheels and pulleys are technically levers. They're just an infinite number of infinitely small levers that are arranged into a circle. But this is another type of mechanical advantage where you can string ropes through pulleys to get your mechanical advantage. In this case, it's the force that I put in is this last rope that's not going to the object that's being lifted. This last rope where I pull on it, that's the amount, however much I pull on it will give this rope some tension. As it goes through the first pulley and then goes through the second pulley, it transmits that tension that I pull with all the way down to this second pulley where the object is hanging. And on the other side of that pulley, if I tie it back up here to this first pulley, I'm just trying to go on the center there, that second tension on the other side of the second pulley or the bottom pulley also lifts this object. So I pull here with 1 T, and inside this machine, it's getting pulled up with 2 T's. And so I can lift something that weighs 100 pounds by only putting 50 pounds of force on this cable over here. And you can do it with 3, and then you have a 1-to-3 ratio. You can do it 4 and have a 1-to-4 ratio, and you can do it with all kinds of things. These are called block and tackle systems. They're also, they're useful. We use them all the time. We use these ideas all the time in the world, but not in quite that same way. This last one actually has to do with some of the practical things that you can see with torques. And I think I talked about this earlier in this class. If you put an object in your hand and then you feel that tendon in your crook of your elbow that's holding your bicep to your lower arm, it's very tight there. For just the weight of your arm, it probably puts 75 pounds of force into those tendons on your muscles. And then if you put something in your hand heavy, it even causes those muscles to tighten up even more. You have the same situation going on in your back and everywhere else. There's muscles and bones being held together by these tendons at different positions, and causing the muscles to have to lift a lot more or to apply much more force than needed. So in this particular arm, you've got the weight of the book, you've got the weight of the arm, total weight there, maybe 20 pounds at most. And then you got this muscle here, the bicep, which is going to lift it at this tiny little distance from the rotational point. It's like trying to hold open the door without going through it, right? So you have to put a lot of force there, and it's like 100 pounds or more. And the free body diagram looks like this, right? The weight of the arm, you have the weight of the book, and then you have the force of the bicep up, and you have the force on the elbow down. And they don't ask us to calculate anything for the force on the elbow. So we might as well make our rotation point right there so that nothing, we don't have to use it at all. So it just kind of goes away in the torque equation, for example. And that's exactly what they're going to do. You're going to have a torque from the force from the bicep that's going to cause a counterclockwise rotation. So this torque from FB is going to be a positive one. The torque from the weight of the arm, that's obviously going to cause a clockwise rotation. So that's definitely going to be negative torque. And then the weight of whatever they're holding, the book in their hand out here, is also going to cause a rotation that is clockwise, and therefore going to be a negative torque. There they just talked about the fact that standing up straight minimizes torque. You always have lots of torque in the muscles in your back because you have a lot of muscles coming in at really sharp angles. So if you bend over at all, you increase that stress in your back, stress in the tendons, stress in the ligaments, stress in the muscles. Even leaning over just a little bit changes that angle so much more to make it so much harder to support your back. Here you can kind of see those extreme angles. Here's the weight pulling on your upper body, and the muscles that are trying to straighten you up and keep everything going are pulling in this direction. Right? That's a bad thing for your back. You've got essentially this really bad angle for pulling on muscles, and a lot of them happen in the lower back, which is why a lot of people feel pain in their lower back when they've been lifting and moving things around a lot. And that takes us to the end of chapter 9, I believe. Yep. So what's the end result? The end result is that this looks very much like forces and accelerations, some of the forces, but in this case it's torques. some of the torques. Forces equal to mass times acceleration causes linear acceleration. Torques cause angular acceleration, which we'll learn more about next time. Any questions or thoughts or ideas, concerns?
Nothing that I can think of.
Go. Well, if that's the case, then we will end this meeting and send you on your way. Have an enjoyable couple of days, and we'll see you on Wednesday.
All right, I'll see you.